Hello, this is Dr. Miller going over the pre-lab questions for Lab Activity 5.1. Please refer to your email as to when this is due. So, it says using the CRC Handbook of Chemistry and Physics, record the literature values for the specific heat capacity of the following substances. Well, rather than use the handbook and rather than having you look up your own values on the internet, let's use all the same values. So, I'll give you what values to use. So, for aluminum, the specific heat capacity is 0.900 joules per gram degree Celsius. You can also see this in grams per Kelvin, but since our thermometers measure in degrees Celsius and we're looking at change of temperature, so the difference between the change in Celsius and the change in Kelvin is exactly the same because the units are dispersed the same. So as you move through the Kelvin scale, you make the same increments in the Celsius scale. So we can express it this way. So that tells us if you had 1 gram and it changed 1 degree Celsius, that 0.900 joules would have been exchanged. So for copper, 0.385 joules per gram degree Celsius. Magnesium is 1.020 joules per gram degree Celsius, and zinc is 0.387 joules per grams degree Celsius. Joules, of course, is a unit of energy. So these are all obtained from laboratory experiments. So if you go on the internet, you may see slightly different results published, such as copper. You might see it as 0.386. So these are not theoretical values. These are literature values based on experiments. So now we're going to look at number 2. Record the literature value for the enthalpy of solution of ammonium nitrate. So what this says is that there's an exchange of energy in the form of heat when ammonium nitrate is dissolved in water. So that's a term that you need to become familiar with, enthalpy of solution. So something is dissolved in water, there's an exchange of heat. That exchange may be as the bonds are being broken, as the ammonium nitrate, which is NH4NO3, breaks into the ammonium positive cation and the nitrate negative anion. There is either a release of energy in the form of heat or an absorption of energy in the form of heat. And so that can be measured by measuring how much we actually dissolve and the change in temperature in the surroundings. So you have the system here, the system being the chemical, and the water is the surroundings. So there's an exchange of energy between the surroundings and the substance. So if the surroundings gets warmer, then this is what we call exothermic. If the surroundings get warmer, if the heat leaves the system and goes into the surroundings, if the water gets warmer, then it's exothermic. If the water gets cooler, the heat leaves the water, the surroundings, and goes into the compound to break apart the bonds, then it's endothermic. So the values are expressed differently. If it's exothermic, that says it's exiting the system, going into the surroundings. So exo, think about exit, it's exiting, and we indicate this with a negative sign. If this heat, the energy is going into the system from the surroundings, it's endothermic, is going into, so into, and we indicate that value with a positive sign. So this is just telling us direction. Don't think about it being a negative value. Don't think about it as being less than 0. It's a value above 0, but we're indicating the directionality of the energy exchange with either a negative sign or a positive sign. So these are directional signs. So don't think about them as being on an absolute scale of less than 0 or greater than 0. It's telling us which way the energy is flowing. That's kind of hard to think of, because if we have a beaker and we put the powder in here and we got the water, it looks like it's all same system, but we have to think about what is our system and what is our surroundings. And chemists call that the system and the surroundings, the universe. So in this case, the universe is the beaker and the water and the compound. So the compound is the system, the surroundings is the water, and we may even sometimes include the beaker, but we assume basically that we're talking about the water. So now that's the concept behind the enthalpy of solution. Now let's look at the literature value, and that value is positive 25.7 kilojoules per mole of substance. So that's how much energy will be exchanged for a whole mole of that. So we know that we can change mass into moles, and so if we had a whole mole of this and we dissolved it, we could get this much energy exchange. Now you need to think, would the water, because it's endothermic, would the water, it will be, I just told you it's an endothermic process, so what would you expect the water temperature to increase or decrease, and why? So you need to think about that. So then let's look at question 3. Calculate the amount of heat needed to heat a 100 gram sample of distilled water from 25 degrees Celsius to 65 degrees Celsius. Well, we're going to think in terms of energy, and there are two different forms of energy that two different units that we use. Well, actually, there's a lot more than that. There's BTUs, but you could think calories, or you can, with a capital C, or you can think, or a little c. There's 1,000 little calories in 1 calorie with a capital C, and these are food calories. This is a chemist calorie. So 1,000 of these to make 1 of those. Or you can think in joules, and that's how we like to think too. So when we're thinking about water in this particular lab, we're thinking in joules. So there's a specific heat capacity of water. So we need to think about distilled water, and that heat capacity is 4.186 joules per gram degree Celsius. So if we had a whole gram of water and we put some heat into it, we would need 4.186 joules of heat energy to raise it 1 degree Celsius. So 1 gram, 1 degree Celsius. If you had 100 grams and you wanted to raise it 1 degree, you would have to take 100 times this. So it asks, if you had a 100 gram sample and you're going to raise it this much, how much heat would it take? So 4.186 joules per gram degree Celsius times, now we're going to take it times 100 grams, and so our grams will cross out, times the degrees we need to change. So we need to take 65 minus 25, and we're going to exchange 40 degrees. So times 40 degrees Celsius. And we're going to raise it up. So we just need to do the math then and calculate how many joules. So joules of heat. So you'll see if we cross out the grams and we cross out the degrees Celsius, we end up with joules. So that's how to solve this problem. Okay, going on to number 4. So a coffee cup calorimeter is styrofoam cups nestled into each other so that you can contain the heat, so you're not losing a lot of heat past the surroundings, which is the water. So we're going to heat some aluminum, and then we're going to see that it loses its heat when it's placed in room temperature water, or whatever the water is. The water is going to increase by 8.1 degrees Celsius. It's the surroundings, and the sample is going to lose that much heat. So it says that 2007 joules of heat is removed. So let's go back to page 1, and we see our specific heat of aluminum is 0.90 joules per gram degree Celsius. So that would be the literature value, but it's asking us to calculate the specific heat capacity. So now we're going to calculate the value and compare it to the literature value. So now we have how many joules? We have joules equals 207 joules, and the grams was 28.4 grams, and the temperature changed, so we can indicate that with delta T equals 8.1 degrees Celsius. So we know that heat capacity is expressed in joules per gram degree Celsius. So we need to set it up. So we have joules, 207 joules, divided by the grams, 28.4, times the degrees changed, and that would be degrees Celsius. So that's how we solve that. So 207 divided by 28.4, and then 8.1 is also in the denominator. So you're going to get a value, and you're going to then have that value, and then you're going to calculate the percent error. So remember, that's experimental value. So the experimental value from number 4 minus the literature value, which we got on page 1, divided by the literature value times 100% will give us the percent error. And then would you be confident using this particular calorimeter? So how close were you to the literature value, and what was your percent error? So you'll evaluate that and then use that to rate your confidence in using this particular calorimeter for further testing materials, and why or why not would you not use it. So that concludes this pre-lab.